Resistors in parallel are a little bit harder to go through, but we can get through this. So one thing to absolutely remember for resistors in parallel is that charges, individual charges, can only go through one loop at a time. If there's a branch, also known as a junction or a split, some of the charges have to go one way, the other set of charges have to go the other way, right? It's just like any fork in the road. So the current splits. The total current is going to be the sum of the currents of the branches, which makes sense, right? If I have a big, huge river and it branches, some of the water goes this way, some of the water goes this way, but all of the water, if it comes back together, is going to be the same as when it came from that big river. Because the charges can take only one loop at a time, the voltage drop across each branch is going to be equal to the voltage drop in total is going to be equal to the VEQ. As the number of branches increases, the current increases because more charges can be processed. So think about the checkout line at CVS or post office. You're all coming into one line, and then you just go to the next available register, right? Think about the registers as the the resistors. The more registers I have open, it doesn't matter if everybody's really slow as a cashier, you're just going to be able to process more people. So branches that have a higher resistance, it's going to be like a slower cashier, will have a lower current because you're not going to be able to process as many people coming through. So because my current increases the more resistors I have in parallel, my REQ is going to be different than the total REQ for series. So the formula for that is 1 over the REQ is equal to the sum of 1 over the individual resistors. And what's really important is that you have to remember that in the end, you've solved for 1 over REQ. So you have to flip it. You have to take the reciprocal of that to get the REQ. And then again, the current at each branch is going to be equal to the VEQ over the individual resistors. Again, it'll make more sense as we go through it. So our first example, I have two of the same resistors, right? So oftentimes it will look like this, where I have it coming down, and I have the choice either to go down this pink branch or to go through the blue loop. So we're going to be looking at things one at a time once we figure things out. So again, same thing. I have to first find my VEQ, my REQ, collapse that into one single circuit, so I have the I total. Right? So again, same as something in a series. But because these are in parallel, I don't just add 6 plus 6, it's actually going to be 1 over my REQ is going to be equal to 1/6 plus 1/6, right? 1 over this and 1 over this. So 1/6 plus 1/6 is equal to 1/3. So my 1 over my REQ is equal to 1 over 3. So I have to flip both, take the reciprocal, and so I get my REQ is equal to 3 ohms. My VEQ, always simple. All I have to do is add these two together, so my VEQ is 60. So again, now I get my VEQ and my REQ. I can find my current, which is 60 divided by 3, or 20 amps. So coming out of this, I have a current of 20 amps, and it's going to split. Some of the current is going to go this way, some of the current is going to go this way. When they come back together, they're going to have a current of 20 amps again. And at each branch, I'm going to have to drop 60 volts worth of my power, right? So I had 60 volts here, I'm going to drop 60 volts here and 60 volts here, because it doesn't matter which loop I take, I have to, by the end of the loop, finish and use up all of the power that was given to me. So because each branch has the same resistance, right? It's like two cashiers that are working at the same speed, they're going to process the same number of people coming through. So what I first start out with, the other one I knew what my current was. Now what I'm doing is I'm figuring out what my total voltage drop is. My total voltage drop has to be 60 volts. And so I can divide my 60 volts by my ohms to get my current, which will be 10 amps. Okay. Here it was easy to figure out because they're the same resistance, but most of them aren't going to be that easy. For example, the next one. I have two non-equal resistors. And here's a way of showing it where they're another way of showing a branch circuit, right? So I have a wire coming here, and then it physically splits into two things. These are not the same resistance, and so I have to then figure out what's going on. Still the same steps. My 1 over REQ is equal to 1/6 plus 1/12. My least common denominator is 12. So again, 5th grade math. So 1/6 becomes 2/12. Now that they have the same denominator, I can add these, and this becomes 3/12. So my 1 over REQ is equal to 3/12. I flip both. So my REQ becomes 12 over 3, and then I reduce and add my units. So REQ is equal to 4 ohms. So one thing to remember is that in any parallel set of resistors, the REQ is always, always, always going to be less than any of the individual resistors, right? So my total REQ is going to be equal to 4 ohms. Each of these is greater than 4 ohms. Even in my first example, my REQ was equal to 3 ohms, and that's less than either of the individual resistors. So if you stop at this point and you just make sure, oh wait, my REQ, yeah, it's got to be lower than any of these. If it isn't, then you've done something wrong and you should stop. So now I can think of this as a simple circuit, right? It's this equivalent of having one battery source of 60 volts and one resistor of 4 ohms. So my I is going to be V over R, so it's going to be 15 amps. Now I go back to my original circuit. My charge can either take the red route or it can take the blue route. So we're going to look at one route at a time. So the first one is the red route, right? So I have to pretend that this is just one circuit. I have a 60 volt battery. I have a resistance of 6 ohms. I have to drop 60 volts worth of current. And so the current that's going, 60 volts worth of power. So the current that goes through this is going to be 10 amps. Right? So here with parallel, I always know my resistance. I figure out what my delta V should be. And then from that, I figure out my current. For something in series, I know my current, I know my resistance, and I figure out my delta V. So you always have two of the three variables. Here it's always the delta V. So that's how I figure out my red circuit. And then in my blue circuit, I treat that like it's just one circuit by itself. 60 volt power source. I've got my resistor of 12 ohms. I know that my delta V has to be 60 volts, and so my I has to be 60 over 12 or 5 amps. And this makes sense, right? We said that if you have a faster cashier, 6 ohm resistor, it's going to be able to process more people. In fact, if I have someone who's twice as slow, my 12 ohm resistor is twice as slow, it's going to only be able to process half as many charges. Right? So this is looking at them individually, and then I put them back, and this is what it would look like in the picture, right? So my red loop going this way, and my blue loop going this way, and then they join again here. So my current was 15 amps. Here, 10 amps goes here, 5 amps go here. When they combine, it's 15 amps again. In each loop, I drop 60 volts, and my resistance is different, right? Now, let's see if you're up to 3 resistors. So now I have 3 different resistors. I have a 2 ohm resistor, a 6 ohm resistor, and a 3 ohm resistor, and 2 batteries. So again, I find my VEQ and my REQ. 90 plus 30 is equal to 120. That's always easy. 1 over REQ is equal to 1/2 plus 1/6 plus 1/3, right? I put 1 over these. Least common denominator is 12. So 1/2 becomes 6/12, 1/6 becomes 2/12, and 1/3 becomes 4/12. Now that they have the same denominator, I can just simply add these up, and this becomes 12 over 12. Then I flip. So 1 over REQ equals 12 over 12, REQ equals 12 over 12, and then I simplify. So the REQ is equal to 1 ohm. And I'm going to stop and say, wait, let me just double check. Is 1 less than 2, 6, and 3? Yes, it's less than any of those. So now this complicated circuit right here is the equivalent, the same as having one battery source of 120 volts and one resistor that's 1 ohm. So then I figure out my I, my current, which is going to be 120 divided by 1, or 120 amps. So again, seeing this is the same thing as seeing this, my total current has to be split into 3 parts. So one of the things that I should remember is that the 2 ohm resistor should have the most current. It's the fastest cashier. The 6 ohm should have the lowest current. It's the slowest. And the 3 is somewhere in between. And my delta V has to be the same across each of the 3 resistors. So again, I'm going to look at it one at a time. First one is my red one. So I look at it as a 120 volt circuit going through a 2 ohm resistor, which should generate a current of 60 amps, right? Because 120 divided by 2 is going to be equal to 60. Then I take my green circuit, it's 120 volts, and it's going to be pushing through a 6 ohm resistor. That should be able to generate a current of 20 amps. 120 divided by 6 is equal to 20. Voltage divided by resistance is equal to current. And then finally, my purple circuit, again, how far it has to go really doesn't have an impact on this because these are really small circuits. 120 volt going through a 3 ohm resistor, I'm going to be able to push through a current of 40 amps. So again, yes, my 2 ohm resistor had the highest, my largest current. My 6 ohm resistor had my smallest, and my 3 ohm resistor was somewhere in between. And then if I want to bring that back to my original circuit, my total voltage is going to be, sorry, my total amp is, that should be 120 amps. I need to correct that. Here, my voltage that I'm dropping is 120 volts across each of the resistors. And then I'm simply going to divide my voltage divided by my resistance to get my current. 60 amps, 20 amps, 40 amps. So the delta V stays the same because my resistors are different. My current is going to be different. And then all of these currents come back, and that should equal the 120 amps. And let me just correct that on camera right now. So this should be A here and here. Apologies.